Lesson 4-5, Geometric Sequences. Again, a sequence is an ordered set of elements that follows a pattern. A geometric sequence is just a sequence that is found by multiplying each term by a constant called the common ratio. Now, there are two formulas associated with geometric sequences. The first one, a subscript n equals a subscript 1 times r raised to the n minus 1. That one is used to find a specific term, actually to create the sequence if you're given the first term. The recursive formula would be like the rule you can use to find a specific term of the sequence. So let's take a look at an example. Here we need to determine if the sequence is a geometric sequence. If so, find the next term. So if we go from -1/4 to 1/2, from 1/2 to -1, from -1 to 2. If I were to multiply each number by -2, I would get the next number in this sequence. So yes, this is a geometric sequence, and this would be the next term. 2 times -2 would give us -4. Next we have -10. Or not -10, we got 10, we got 3 1/3, we got 1 1/9, and we got 10/27. Now this might make it a little bit easier if we rewrote this. So this would be 10, 3 times 3 is 9, plus 1 is 10, so 10/3, 10/9, 10/27. And this is really 10/1. So really, I'm multiplying every fraction by 1/3. So yes, this is a geometric sequence. If I multiply 10/27 times 1/3, I would get 10/81. Next, here we want to determine if the sequence is geometric, arithmetic, or neither, and then find the next 4 terms using a pattern. So if it's arithmetic or geometric, then we're going to find the next 4 terms. So we have 456, 45.6, 4.56, 0.456. Well, here I know I'm dividing by 10 each time because the decimal point keeps moving to the left. So I'm dividing by 10 or multiplying by 1/10. So this one would be a geometric sequence. And that means the next term would be 0.0456. Next would be 0.00456. Then we would have 0.000456 and 0.000456. Next one, we have 3 to the 3rd power, 3 to the -3rd power, 3 to the 3rd power, 3 to the -3rd power. Now it just keeps alternating back and forth with that one. So 3 to the 3rd power is 27. This would be 1/27, then 27, then 1/27. That would be neither. And then if we were to continue the sequence on that one, then it would just be 3 to the 3rd, 3 to the -3rd, 3 to the 3rd, 3 to the -3rd. Next, we got 0.07, 0.08, 0.09, 0.10. So this one would be arithmetic. And each time they're adding 0.01 to it. So that means the next term would be 0.11, 0.12, 0.13, and 0.14. Next, we have 3/4, 1/2, 1/3, 2/9. For this one, let's see if this would be 3/4 to 2/4. And then from 1/3, so that would be, we had all common denominators on that one. So let's see if I did 2/6 minus 3/6 is -1/6. That would not be an arithmetic sequence, because again, if I just did 2/4 minus 3/4, that gives you a -1/4. And then if I did 2/6 minus 3/6, that gives you a -1/6. They're not the same, so it's not arithmetic. Geometric, it could be geometric, because if I multiply the top by 2/3, let's see, no, three halves. So if I multiply by 3/2, let's see, to find if it's a geometric sequence in the common ratio, I can take the first term, so 1/2, times the first term, the previous term, which is 3/4. So if I multiply that by the reciprocal of 4/3, that'll give you 2/3. So if I multiply everything by 2/3, 3/4 times 2/3 is 6/12, and 6/12 is half. Half times 2/3 is 2/6, which is 1/3. 1/3 times 2/3 is 2/9. So this is geometric. And then the next four terms, 2/9 times 2/3 is 4/27. After 4/27 comes 8/81. After 8/81 would give us 16/243. And then the fourth term, the fourth one after that would be 32/729. Next, I have 3/2, 5/2, 7/2, and 9/2. I'm adding 2/2 each time, so that would be arithmetic. That means the next terms would be 11/2, 13/2, 15/2, and 17/2. Next one, 1/4 to 1/9 to 1/16 to 1/25. Now for this one, I can see that the denominators are all perfect squares, and the numerator is all 1. So for this one would be neither, because there is nothing that you're adding or multiplying each time. But the next one would be 1/36, 1/49, 1/64, and 1/81, because again, the denominators are all perfect squares. Sample problems B. Here we want to find a specific term of the geometric sequence. So we're going to use the formula given. We're going to find the 10th term, so 10 is going for the n. So a subscript 10 equals the first term. The first term is -128. And we're going to multiply that by the common ratio, which is 0.5. And we're going to raise that to the 10 minus 1, which is the 9th power. So we're going to use our calculator for this. So I have a -128. And we're going to multiply that by 0.5 raised to the 9th power. And that's going to give us a -0.25. Next, we find the eighth term, so it'd be a subscript 8 equals the first term of 1 times the common ratio of, we're going to have to find the common ratio. So if I did negative 125 divided by negative 5.25, just looking at this, this should actually be a comma here. So it goes from 1, negative 5, 25, negative 125. So the common ratio would be a negative 5. And then I would have 8 minus 1. So on our calculators, we would have 1 times parentheses negative 5 raised to the 7th power. And that's going to give us 78,125. Then next one, find the 7th term. So a subscript 7 equals the first term of 3, the common ratio. Here I would do 0.6 divided by 3, and I'll multiply it by 0.2. So times 0.2 raised to the 7 minus 1 power. So on our calculator again, we have 3, and that's going to be times 0.2 raised to the 6th power, and that gives us a really long decimal. So 1.92 times 10 to the negative 4th. So this one would be 0.000192. Because if I took, it was 1.92 times 10 to the 4th. So if I move the decimal point 1, 2, 3, 4 to the left, that's what our sequence, our next number would be. Next, find the 9th term. So a subscript 9 equals the first term of x times the common ratio would be 2 raised to the 9 minus 1 power. This would give us a to the 9th equals 2 to the 8th power, and 2 to the 8th power is 256. So this would be 256x. Next, we're going to be using the recursive formula for the nth term of the geometric sequence, and that formula would be a subscript n equals r times a subscript n minus 1. So for this one, we need to find the common ratio here. So I'm going to take the first term, 1.2, divided by the previous one of 0.3, which is really 12 divided by 3, which will give us 4. So we would have a subscript n equals 4 times a subscript n minus 1. Next, find the recursive formula for this one. I would take 2 over 27 times the reciprocal of negative 81 over 2. 2's divide out. Negative 81 divided by 27 is negative 3. So we would have a subscript n equals the common ratio of negative 3 times a subscript n minus 1. Next, write the recursive formula for the nth term of this geometric sequence. So we can see that the exponents are increasing by 2 every time. Because really this one is actually 0, y to the 0 power. That's how you get that 1 there. So the recursive formula for this one is when I multiply like bases, I add the exponents. So the common ratio would actually have to be y squared, because y to the negative fourth times y to the second power, it'd be negative 4 plus 2 is negative 2. So we would have a subscript n equals the common ratio of y squared times a subscript n minus 1. And our last one, Hilda bought a car for $17,500. Her car depreciated 25% in value each year. What was Hilda's car worth 3 years after she bought it? So for this one, we're going to use an interest formula, but it's declining in interest. So we're going to do the value equaling the principal amount, so the amount she bought it for, times 1 minus the rate raised to the t power. So the account balance, or the amount it would be valued at, would be 17,500 times 1 minus 0.25, and that's for 3 years. Now if I put that in my calculator here, we would have 17,500 times parentheses 1 minus 0.25, which is 0.85, minus 0.85, and we're going to raise that to the third power. That's going to give us actually I did that wrong. Let me edit that. If I did the 1 minus, this would be 1 minus 0.25. Then hit enter. There you would have it, $77,382.81. $7,382.81, and that would be the value of the car after 3 years. So that is our lesson on geometric sequences.